started the chapter 4, which deals with the stereoisomers, and we have learned most of the content. For example, we have learned the enantiomers and the diastereomers and their properties, and we also learned how to assign the stereocenters using the CIP rule, so the ROS, right? And then we learned the concept of the methyl compound and what's the difference between methyl compound and racemic mixture. And also at the end of last lecture, we have learned the resolution, the concept of resolution, and how people did resolutions to separate enantiomers or to separate enantiomers and in the racemic mixture. Okay, there are a lot of things I would like you to keep in mind this time. So first is the nomenclature drill is still open, so there is no time limits, but I would recommend you guys to try it as soon as possible. Okay, and the stereochemistry drill is also open now, so from September 9th to October 11th. Okay, so so I think many of you have already taken the stereochemistry drill, and probably most of you feel that it's much difficult and much more difficult than the nomenclature drill, right? Yeah. So the stereochemistry drill is actually pretty difficult, and I would say it's equal to the level of difficulties of the problems you are going to solve in exams. Okay. And then the problem set number 3 will be open on September 25th. Now finalizing some of the problems I'm going to put on it. Okay, and so after this chapter, after today, you should be able to try the practice problems we put on the Moodle. Okay, so on the Moodle you can find these. So this is Moodle, right? And you can find these problems here. So practice problems for stereochemistry. So it's excerpted from the textbook. So we put on it here so everybody can see it. So when you open it, you can see there are tens of questions like that with the solutions. Okay, so you can try to solve these problems, and you have the answers here, so you can know whether you are right, whether you are wrong. Okay, so I would say if you are really you really solve this problem by yourself and understand the logic and the principles behind it, you don't need to be afraid of the exam or midterm. Okay, and so it will be on the Moodle for you to download. And another, the deadline for signing up the tutorial group is today. Okay, 3:30 p.m. So this afternoon. Okay, be sure to sign up for that. And the formal tutorial session will start on September 23rd, so next week. Okay, and probably one of the most important dates is that the midterm. The midterm 1 will be on October the 9th. All right, so the details about the exam will follow, and I will let you know what's the format, what you are going to pay attention to, something like that. Okay, and it's already, actually, I want to say it's already September the 15th, so it's only 3 weeks apart from the midterm 1. So, and if you are still warming up about this masters, I would suggest you do it quick, okay? And especially from today, so things are going to get very difficult, or much more difficult than the previous chapters, okay? So at the end of last time, we start to give you a review about isomerism. Okay, so we are going to pick that up. So isomers, so constitutional, and what we focus majorly on in this course is stereoisomers. Okay, because constitutional isomers, you guys have learned it in the general chemistry, and really not much to do with this course here. Okay, and for the stereoisomers, we have 2 types. One is the enantiomers, the other is diastereomers. Okay, and for enantiomers, they are mirror image. Diastereomers, they are non-mirror image. And within the category of the diastereomers, we have configurational diastereomers and cis-trans diastereomers. All right, so we've learned this last time. So constitutional isomers, you can have a different skeleton, different functional group with the same functional group in a different position of the molecule. Okay, so this is the enantiomers. They are mirror images to each other, 2R, 3R, and flip that becomes 2S, 3S, which is enantiomers to the original molecule. So for the diastereomers, so it's not 2R, 3R now, it's 2R, 3S. Okay, they are not mirror image, so they have different properties. Okay, and the cis trans is also diastereomers, and pay special attention to this molecule because this is also a methyl compound. All right, so that means although it has 2 stereocenters, it also has an internal plane of symmetry here. Okay, so it's not chiral, it's not an it's a chiral molecule. And okay, so this is something new. So how about we learned that the stereocenter is carbon or an atom with 4 different substituents, right? So how about atoms that other than carbon? Okay, so here we have a tetravalent nitrogen, all right? And the nitrogen has 4 substituents, right? And in this case, 4 different substituents. So its mirror image is this. So they are non-superimposable. Okay, so if you move these 2 molecules close together, you will see that if you flip this propyl group to the right side, this SO is pointing to you, but this SO is pointing back. All right, so they are mirror image that is non-superimposable, so that they are actually enantiomers. So the same applies to the phosphate. So this is the tetravalent phosphate, which has 4 different substituents, right? Hydrogen, methoxy, ethoxy, and a double bond oxygen. Okay, 4 different ones. All right, and then if you look at the 4 different ones, you can see they are actually mirror images to each other, and these 2 mirror images are actually non-superimposable. So we say this phosphine is also a stereocenter, and these 2 are enantiomers. All right, so that is the tetravalent nitrogen and phosphorus. So how about trivalent? So in the case of trivalent, so one of the valency is now replaced with a lone pair, right? So like we draw here. So the lone pair is not any group, right? But it's just a pair of electrons. So for the nitrogen, actually trivalent nitrogen, we do not consider it. It's not considered as a stereocenter because this trivalent nitrogen can flip really quickly. Okay, so if this lone pair is pointing up, so after the flipping, the lone pair will be flipping down. All right, and then because this process proceeds very quickly, so in the room temperature or in a normal situation, the nitrogen is flipping up, down, up, down, up, down. So the conformation is not really fixed. So we do not consider it as a stereocenter. So it is achiral. Okay, consider it achiral. But for the phosphine, its flipping is much slower, and so it's considered configurationally stable. So for example, for this one, the lone pair is pointing up, right? So it's for it to flip and let the lone pair flipping down, this is a very difficult process. So it's relatively stable. So we say this configurationally stable molecule is a stereocenter. Does have has a chirality. Okay, then if it has a stereocenter, then we can also use the CIP rule to assign the stereocenter. Okay, so the trick is that we put the lone pair as the lowest priority. All right, just like the carbon, we put the hydrogen as the lowest priority. For the trivalent phosphine compound, we put the lone pair as the lowest priority. Then we can now assign the chirality of this. So so this you guys may already learned how to do that, but I'm going to show you the one last time. So okay, here. So if we put this lone pair as the lowest priority, then the direction we are going to look at this molecule to assign the stereocenter is from the bottom, right? Put the eyes here, right? So what we see from the bottom is that we have a funnel pointing to you. That is up, right? On the right of the funnel, we have the we have a propyl group, which is CH2, CH2, CH3. And on the left, pointing to you, is CH3. Okay, then we need to figure out what's the priority within these three. So for this carbon, this is a carbon with 1 carbon substituent, 2H. And for this methyl, we have a carbon with 3H. And with this one, it has a double bond on it. Okay, it's a carbon with 3 carbon, right? Because double bond is considered 2 carbons. Okay, then we can say this is the highest priority, this is next, and this is the lowest priority among these three. So the direction should be this, this, this. So it's R, right? Because it's your right hand. So when you assign this, it's R. So the full IUPAC name should be R methylpropylphenyl phosphine. All right. So it's a pretty easy one. All right. So basically that's all for the chapter 4, the content for chapter 4. So at the end of this chapter, I'm going to show you some pretty interesting facts about chirality in nature, just as relaxing, you know. So for example, in nature, there are a lot of chiral molecules, okay, and there are a lot of enantiomers. For example, you have the carbon, okay, and based on the difference of these stereocenters, you have R carbon or S carbon, okay, and you can see because they are enantiomers, so their optical activity are opposite to each other in number, right? And then one of them, for example, the R carbon smells like a spearmint. The other way, the other one, the other enantiomer smells like a caraway seed. So actually, when I was at TA in graduate school, so they have an experiment asking the undergraduates to smell these two compounds and write down to let them learn the concept of the chirality and the difference. So and also ask them to explain why these two enantiomers smells different. Okay, it's quite simple because it's your nose. All those proteins that's in charge of the recognition is kind of chiral biological machinery. Okay, and these are enantiomers. So the interaction between enantiomers and your nose, the recognition power of your nose is actually a chiral interaction. Okay, and as we already learned, that chiral interaction has different energy. For example, like your chiral feet with chiral sneakers, right? So they actually interact with your protein differently, so they smell different. But the interesting thing is that, so in a class size about, like, I would say 50 students, almost there are always like 5 to 10 students who cannot differentiate between R carbon and S carbon. Okay, so to them, they smell exactly the same. So that's the magic thing about like a human body or the biological system, is that not only are they chiral, so everybody's recognition power is actually different because you have different DNA and thus you have a different biological machinery. Okay, so if you have a chance, you can try to, if you have a chance to have R carbon and S carbon, try to smell them. Okay, it's refreshing. Both of them are pretty refreshing. All right, and so if we talk about the chiral interaction between a molecule and your human body and your proteins, something like that, so then automatically we think about drug, right? So because drugs are usually molecules, and if your drug has these stereocenters, then you have it has to have some interaction with your proteins, right? So as I said here, so although enantiomers have the same physical properties, they usually have different biological activities. This is because your human bodies or living organisms are chiral. Okay, for example, if your enzyme in your body or in biological system looks like this, all right, and the R enantiomer fits right in there, okay, the square to square and triangle to triangle, the ball shape to ball shape, right? But now with the same protein acceptor, if you use the S enantiomer of this molecule, right? You can say they don't fit anymore. All right. So the property of drugs depend on the stereochemistry. That's because your biological system or living organism proteins are chiral, and even when R enantiomer fits, that means the S enantiomer may not fit. Okay, so that actually causes huge problems. Some of you probably already learned this story or this very tragedy. All right, so this molecule called celidomide. Okay, it has a chiral center. All right, so this one and this one, and they are enantiomers to each other with a mirror image between them. Okay, so what's the assignment here? Is this R or S? That's the quick questions I want to ask you. So it's very simple, right? I won't write it down. I'm just talking about it. So the hydrogen is hidden behind it. So that means if we put the hydrogen in the back, this is what we look at to assign the stereochemistry. So nitrogen, carbon, carbon, nitrogen is highest. So this carbon has 2 oxygen. This carbon has 2 hydrogen. So that means this is the next. So that means it's this circle clockwise. That means this is R celidomide, and this is S1. Okay, but in the 1950s, so people didn't understand or recognize that the chiral-chiral interaction between drug and your protein that deeply. Okay, so what they did is that they find that this drug works on somebody or some pregnant woman. So they think, okay, let's give them to all the women that is pregnant, has some morning sickness to treat, and then tragedy happens. All right. So so it is given as a racemic mixture, but later it is found that a woman who took this drug had an extremely high occurrence of miscarriages and babies with born with abnormalities like the Vacomelia. So like this, totally tragic. So then deeper research on a deeper level point out that the S enantiomer of this molecule is actually embryonally toxic. So that's really bad. So which affected almost 10,000 babies. So that means that because our protein or biological system is chiral, so the R1 is good for people, but the S1 is now very bad. It causes very bad situations for embryos. Okay, so actually after this tragedy, the incident shaped more rigorous government policies. So if you are really interested about the significance of chirality in pharmaceutical industry, so I found this paper, and you don't need to know organic chemistry that much, but it's a kind of a half policy, half scientific papers, so you can read into it and find out what people have done since all these tragedies, and what's the policy and what's the government's attitude towards chiral drugs. All right. So, so the major topics of chapter 4 I have listed here. So we have learned the nomenclatures, especially for stereochemistry, and we have learned the concept of chirality and concept of enantiomers, diastereomers, and a special compound called meso. And we also learned that optical activities is an important physical properties that's related to enantiomers. And we also learned how people do resolution to separate enantiomers, and especially this how do you name the stereocenter configuration, especially how to differentiate between R or S using the CIP rule. All right. So after finish, and that's the summary of topics listed here. Okay, I'm not going to details again. So basically, so we start with the non-superimposable test and the mirror image, and the F2 mirror images are non-superimposable. They are chiral molecules, and then the opposite is achiral molecules. And the stereocenter is probably one of the most important concepts we have learned so far, and 4 different substituents. Okay, and you can assign R or S to stereocenters. But one exception is that stereocenters do not guarantee chirality is meso compounds, which have stereocenters, but also has an internal plane of symmetry. So it's achiral. And enantiomers, same chemical and physical properties except optical activities. So enantiomers have opposite optical activities. And if the enantiomers interact with other chiral entities, so that's chiral-chiral interactions. So it's going to be different. And the diastereomers, so basically they are non-mirror image and totally different. Okay, different chemical and physical properties. And because they have different chemical and physical properties, we can use them to separate enantiomers by turning the enantiomers into a pair of diastereomers and then separate it. All right. Okay. And so that's pretty much for the chapter 4. Okay. Please, I remember to do the stereochemistry drill, and also stereochemistry drill is full credit. Okay, that's 5 points into final grades. All right. So think about it. You just need to do 10 problems to get 5 points. So that's pretty easy, right? Much easier than midterm. Okay. And so next we are going to start chapter 5. So that means we already finished the warming up of this course. Okay. And so the learning outcomes I have listed here for chapter 5. All right, so we are going to first review and understand the thermodynamics and the kinetics of reactions in general. So these are 2 concepts you probably have already learned and understand in your general chemistry course. All right, so we are going to review it in the context of organic chemistry. And we are also going to learn how to draw mechanisms, all right, showing electron flows with correct understanding and notation. So that is the very base foundation of organic chemistry. So how do you describe a reaction, right? How do you tell other people what's the mechanism of this reaction? So we are going to learn in this chapter. And there is also some stereochemistry issues of alkenes we are going to recognize and assign, all right? Because alkenes, it does not have R or S situation, but has EV, or what we call cis-trans situation. And the most important one, and the most important things for the rest of this semester, is to explain and rationalize the mechanism of various reactions of alkenes. So we're finally going to learn some new reactions, okay? And what we expect of you is that at the end of this course, you are going to apply all those reactions you have learned in this course to the synthesis of real molecules, not real, like molecules on paper, okay? For real molecules, you need to figure out the lab course. And also, if you are interested in going to organic chemistry research group, then you can figure out how to make molecules with real. All right. So alkenes. So alkenes are hydrocarbons with a CC double bond. Sometimes we also call the alkenes olefins. All right. So actually, in the natural world, alkenes are included in many naturally occurring materials and vitamins and monomers, polymerization. So you probably already know ethylene, right? It is a very important polymer monomer, and there are huge number of polymers that based on the polymerization of ethylene. And you have a vitamin A1, a natural molecule, right? So called retinol because it's relatively good to your eyes. Okay, so you can see it has 1, 2, 3, 4, 5 double bonds conjugated with each other. All right, and then you may see, oh, okay, so this is the beta carotene, and it has color, and it's from carrots. All right, it's an orange pigment because it has so many double bonds conjugated to each other. And so you may wonder, oh, why does this look so much like the vitamin A1, right? So that's why your parents tell you, oh, eat more carrots because you can get vitamin from the carrots, right? So yeah, that is true. Actually, beta carotene is a vitamin A precursor. So if you let's say ideally, if you eat more carrots, you can have more vitamin A1, which is really good for your eyes. All right. And we have a more complex molecule. For example, this huge molecule of Taxol only has one alkene here, which is tetra substituted 1, 2, 3, 4, 4 substituents, right? So it's isolated from the yield tree, okay, and it's very high potent for cancer. It was once a star molecule that organic chemistry groups from all over the world are trying to make this in a large quantities so people can test the biological activities of this molecule to treat cancers, okay? And this is another good opportunity for you to assign stereo centers, right? Because there are, I would say, more than 10 stereo centers in this molecule, and each one should be assigned ROS. And then I would say if you can successfully assign all these ROS in this molecule, you are pretty good at this, okay? And no need to worry about the exam. Not all the exam. To worry about the assigning stereo centers part of the exam. Okay, you still need to learn other parts. Okay, so one important thing about alkenes is that alkenes are unsaturated. Okay, we say alkanes like the pentane, like C5H12. So it has the maximum number of hydrogens for its number of carbons. Okay, every carbons 2 carbon, then all the other are hydrogens, right? So we say pentane, for example, and also the cyclohexane are saturated molecules, but molecules with less than the maximum number of hydrogens. For example, this carbon could have 2 hydrogens, but it forms a double bond, so it's not have the maximum number of hydrogens. So we say these alkenes are unsaturated. All right, and all the alkenes are unsaturated. For example, compare with cyclohexane, right, which is a saturated molecule. Cyclohexene, which has a double bond, now alkene, is unsaturated. All right, so this concept, a small concept, but need to keep that in mind. So I'm not going to show you the full set of IUPAC nomenclature of alkenes. All right, I'm just going to review it very briefly. So the first step, like the alkenes, right, you find the longest continuous carbon chain. But in alkene, you need to pay attention to that. You need to find the carbon chain that contains the double bond. All right. For example, this molecule, you name it as a pentene. All right, not as a hexane, because only you name it as a pentene will you include this double bond in the carbon chain you counted. All right. If you find the longest carbon chain, 6 carbon chain, but double bond is outside of the chain, so you cannot name it as a hexane, but as a pentene. All right, 2 methyl 1 pentene. Okay, and the step 2 is that you number carbons in chain so that double bond. So the double bond is what we care about. Okay, have the lowest numbers. So for this linear molecule, you can either put the number 2 on the alkenes. You can also put the number 4 on the alkenes. They're the same molecule. But what we do is that we put number 2 because we want to put the CC double bond as the lowest number. And the rings have cyclo prefix. Okay, and if you have 2 double bond, they are called diene, and the 3 double bond triene, many double bond poly, which we won't deal with in this course. And so, for example, this cyclic structure, they both have a ring structure. So cyclo, right? And also it's a diene, so we call it a cyclohexa 1,3 diene. Got it? Okay, some other things. So alkenes can serve as substituents. So you need to be familiar with these nomenclatures or common names for these alkene substituents. For example, if you have a long chain or a group that's substituted with CH2 with a double bond here, we call this a methylene group. All right, and if the substituent is CH2, then we call it a vinyl group. If it's CH2, CH2, so 3 carbon, we call it an allyl group. And based on these substituents name, we can have common names for a lot of molecules. For example, this is 6-member ring connected to a CH2 methylene group. So we can call it a methylene cyclohexane. Again, if we have a vinyl group substituted with chloride, we can call it vinyl chloride. So if there's a bromide, vinyl bromide, right? And then again, if the allyl group is substituted with OH, allyl alcohol. What if this OH is chloride? So allyl chloride, all right? These are common names. And another concept is the vinylic and allylic carbon, okay? Vinylic carbon is sp2 in nature. So all these carbon, like I pointed here, vinylic, okay? These two, okay? Allylic is the is the carbon neighboring the vinylic carbon, okay? It is sp3 in nature. So for example, especially these allyl group, so these are the allylic carbon. And also, by extension, this CH bond is called the allylic CH bond, okay? And for the electronic structure of alkanes, let's do a brief review, all right? So we have the sp2 orbitals of two carbons, okay? And the sp2, like this green one and the red one, they are 120 degrees apart from each other, right? It's a planar. And then if these two sp orbitals form a bond, share electrons head to head, okay? Head to head. So this is a sigma bond, okay, formed here. And then there is another orbital, the p orbitals, that is perpendicular to the sp2 orbital, okay? And once the sigma bond is formed, these two p orbitals are really close to each other now, and they also like to share electrons. And they don't share electrons head to head, they share electrons side by side, okay? And those side by side shape a bond, what we call is a pi bond, all right? So for the sp2, for the alkenes, we have a sigma bond formed by sp2 orbitals, and we have a pi bond formed by the p orbitals, okay? And these two bonds form the double bond, as we call it. And as we learned in the last chapters, so pi bond is much weaker than the sigma bond, but the double bond is much stronger than the single bond, okay? If you don't understand what I said just now, you need to go back to chapter 1 and look at the corresponding slides and see what's happening, okay? So you cannot say a pi bond is stronger than a sigma bond, because a pi bond plus sigma bond, which is double bond, is stronger than sigma bond, which is a single pi bond, okay? Just be clear about these things, crystal clear, all right? So for example, in a simple ethylene molecule, all right, you have a bond angle H, carbon H, almost 120 degrees, slight deviation, and you can see the pi bond. You can see the double bond is 133 pm. Okay, and so that's the structure features, and it's a plain molecule, and so p orbitals overlap to form a pi bond. So I'm going to briefly show you. So in a real 3D model, so you can see it's the ethylene is a plain molecule, all right, and achiral molecule, right, because it's a 2D objects, all right. So too big. All right. So from the molecular orbitals, so its description of a CC pi bond is like you have two p orbitals side by side, right? So this is what we talk about a pi bond, because these two p orbitals share bonding side by side, okay? And it has a plane. The plane is the alkene plane. So it's you have a bonding orbital, then you have an anti-bonding orbital. So you can see the color is different because they are not bonding. So this is blue, this is green. So the non-bonding orbital, that's the concept of it, okay? Because they are of different colors, so they cannot bond. They cannot share molecules. Okay, so this is just a MO description of a pi bond, and we'll come back a little bit later. So compare with alkanes. So the alkene structure is very different. Okay, so as we learned in the last chapters, all the conformations of the alkenes is from the free rotation of carbon-carbon sigma bond, right? Because it can rotate. Then different groups on this carbon can have a different relatively position to groups on this carbon, right? But as we say that because now the alkene CC double bond not only has a sigma bond here, it also has a pi bond. Now the pi bond is side by side. They cannot rotate, right? So if you rotate, you break the pi bond. So if you rotate 90 degrees, so the electron clouds is far away from the electron clouds of another carbon. So it's broken, all right? So unlike alkenes, so the alkenes have occupied pi orbitals here that prevents rotation about a sigma bond. So to put it simply, the sigma bond is actually, in the case of alkene, locked by the pi bond because the existence of the pi bond, the sigma bond in the alkenes cannot rotate freely. And you see the rotation barrier for the pi bond now is 268 kilojoule. Okay, that basically is impossible to rotate because if you recall that the ethane rotation is around 12 kilojoule per mole for this one, OH. Okay, it's 12 kilojoule. That is more than 20 times higher energy requirement. Okay, so to break the lock, to break the pi bond, let it rotate, enormous energy is needed. Okay, and then because it cannot fully rotate, then we have isomers that cannot interchange with each other. So as we learned in last chapter, because ethane has different conformers, right? We know that. But because the CC bond can freely rotate, so at room temperature, normal conditions. So what we observe as ethane is the average of all different conformers because they are interchanged really quick, right? But alkenes cannot interchange really quick. It barely interchanges, okay? So that means one conformation and other conformation, they are locked from each other. So what does that mean? For example, you have two, for the butene structure, you have two kinds of butene structure. One is that the two methyl on the same side, all right, like this, same side. Another one is two methyl on the different side of this double bond, okay? So one isomerism we are going to talk about is called cis-trans. And cis-trans only applies to disubstituted alkenes, like the butene here, okay? And the cis conformer is referred to olefin or alkenes, that two protons, disubstituted olefin or alkenes, that the two protons of it are on the same side of the double bond, like here. We call it a cis to butene. Then the trans is two protons on the opposite side, like this and this. They are opposite side on the double bond, right? So, and these isomers are called geometric isomers. And this is, so you can call it diastereomers. That's good enough, okay? You don't need to tell me this geometric isomers. If you forgot the name of geometry isomers, it's fine. They are diastereomers, okay? Because they are stereoisomers that are not mirror image, okay? These do not look like a mirror, okay? So to break the pi bond, we need a huge amount of energy, right? So they can be done on several conditions, okay? And one is by heating, the other is by light, okay? So the huge energy barrier can be overcome by heating the molecule at high temperature. So by heat the molecule in high temperature, you increase the correlation of different molecules. So the energy it gets is much higher than lower temperature, okay? And once it gets very high energies, then it has the energy to break the pi bond and rotate, okay? So when you heat like cis-2-pentene at more than 180 degrees, the pi bond break, okay? And then rotate and form another pi bond. Then you have a trans-2-pentene. So you can also do this under light, okay? The light can give energy to the double bond. You can understand that in this way, okay? So very prominent examples is that it's actually happening every time, anytime, so it's actually happening now in your eyes if you are not sleeping now, okay? Hope you are not, hope you are listening to me right now, okay? So in your eyes, we have those molecules, right? Vitamin A derived okay, this conjugated chain. Okay, so this opsin is a protein that found in your photoreceptive cell of retina in your eyes, all right, surface of your eyes, okay, and it has a cis double bond here, all right, and then when the light shine on this double bond, and the pi bond break, and it goes to another shape, okay, so this is the cis conformation, okay, configuration of your alkene. Then when it sees light, okay, it becomes straight. All right. So these numerous numbers of these kind of molecules is accepting light in your eyes and in your cell of retina, and this eventually contributed to your recognition of light. The color, the strength of light sensed by your eyes are actually so this transformation is responsible for that. Okay, pretty magic, right? Okay, but it needs to be pointed out that cis-trans designation can only be used for disubstituted alkenes. That means two hydrogen substituents. Okay, only an alkene with two hydrogen substituents can call it a cis or trans. So for example, if you have a tri-substituted or tetra-substituted alkenes, you cannot call it cis or trans. So that is just plainly wrong. Okay, so we need a more broader definition of the isomers of alkenes. So that's why we are going to introduce the concept of EZ system. All right, so it works for all alkenes. Okay, so you can apply EZ system on disubstituted alkenes. That's correct. That's okay. But you cannot apply cis-trans system to tri-substituted or tetra-substituted alkenes. So what does that mean, the EZ system? So here is how we do it. So for each sp2 carbon of the double bond, assign priority. Okay, we use the same principle, the Carr-Engel-Prelog rules, the CIP rules, the same as assigning priority for R and S. So we have a double bond for each. Okay, keep that in mind for each sp2 carbon. So we separate these two carbons. So on the left carbon, we assign whether this group is lower or this group is lower. Okay. Then on the other carbon, we assign between these two, okay, higher or lower, okay? So if two higher priority groups are on the opposite side of the alkenes, we call it E double bond. It's Latin, I believe, and the gegen, okay? It means opposite side, okay? Higher, opposite to higher, that means lower, also opposite to lower, right? Then we have Z double bond. So after the assignment, we found out the higher group of this carbon and the higher group of this carbon, if they are on the same side of the double bond, we call it the Z double bond. Okay, I cannot pronounce it this one, but just remember it's Z. Z is on the same side, E is on the opposite side. All right, so just keep this in mind. For example, let's take this molecule as an example, all right? So we have bromide, chloride, hydrogen, CH3. You don't compare them together, okay? You separate them, okay? Compare them by carbon, all right? So on this carbon, what do we have? We have a CH3, we have bromide. Bromide is definitely higher because bromide has a bigger atomic number, right? And then on this side, hydrogen must be lowest, right? Chloride is much higher. So now you can see the bromide and the chloride, these two higher priority groups are on the same side of the molecule, okay? So we can call it Z alkene. And the IUPAC name should be Z, 2 bromo, 1 chloro, prop, 1 in, okay? So keep this in mind. So when you are asked for a full IUPAC names in exam, stereochemistry is required, all right? So if I give you a chiral molecule or give you an olefins with defined geometry, all right? You need to, besides you assigning the names for 2 bromo, 1 chloropropane, so you need to give me Z, you need to give me R or S for that molecule, or cis trans if it's disubstituted, or if it has a ring structure with both substituents on the same side, okay? You need to give me cis. So only when you give me the full name with these stereochemistry designations assignment, can you get a full points for that problem? All right, keep that in mind. So if you recall the CIP rules, we also have some extension, right? We just learned. So if atomic numbers are the same, compare at the next bond connection, at the first point of difference. Basically, you figure out what's on each carbon, or what's on each carbon, and what's on each, is it CCC or CHH or HHH? Then compare them one by one from the biggest. And if you have multiple bonds, then double bonds, as usual, counted as 2 bonds. So if you have alkene that is substituted with an alkene, then the carbon of the alkene is counted as substituted with 2 carbons. Okay. If you have an alkyne, the carbon is substituted with 3C. Okay. All right. A small practice, and it's pretty simple. So I don't even write it down. All right. Just follow me. Okay. So I asked you to assign the EOZ of this double bond, right? So you assign separately. You consider separately. You have a separator here. Okay, for this carbon, you have 2 carbon, right? They are both carbon, but this carbon is substituted with 3 carbon because it's triple bond, right? But this carbon is carbon HH, so this is higher. Okay, remember that. So this is higher. And for this carbon, you have carbon. This carbon has an O. The other 2 are H, right? So OHH. For this carbon, you have a double bond O. So that means OO, right? So this carbon has OOH. So this is higher. So this is higher. This is higher. 2 higher priority on the opposite side of the double bond. That means it's E, right? Okay. So so this is the E alkene. All right. So now you actually, after we learned the easy system of the IUPAC naming of the stereochemistry, you have learned everything needed to complete the stereochemistry drill. Okay. And again, this is for credit. Okay. If you don't do it, it's really stupid, right? Because it's 5 points for 10 questions. Okay. Just and you can try as many times as you want. All right. This is the easiest thing to get. All right. So I think we will have a small break, about 10 minutes. So we'll come back at 11:27, and we will continue with our chapter of alkanes. All right. So see you in 10 minutes. Talk about the stabilities of alkanes. All right. So so when you consider, because we just learned that the alkanes can have cis or trans, or in more complex system E or Z, right? So different diastereomers of alkanes. So then we, just as when we talk about the conformers of ethane, we say they have consequences in energy, right? So the cis trans or the EZ isomerism of the alkenes also has the consequences in energy. Okay, so so from historical point, how does people start to understand the concept of stabilities? So through reactions. Okay, so for example, we have a trans to butene and cis to butene. Okay, so if we hydrogenate it, so using a palladium catalyst, which is beyond the request or the requirement of this course, but fascinating catalyst. So you can say you put 2 hydrogen into this double bond and this double bond, so we get butane. And think about it. The product for the hydrogenation of trans and cis alkenes are the same. They are both butenes, right? So that means the product energy is the same, butane. Okay. So what people found out is that when the energy heat of the cis hydrogenation, the hydrogenation of cis alkenes actually release more heat. Okay, so that means the cis olefin is more unstable, is less stable than trans, right? Because we have the same energy of the product. So if the energy of the starting material is higher, you release more heat because the energy difference is higher, right? For example, the delta G cis is higher than delta G trans. Okay, the energy released during this process higher. So that means the cis is less stable than trans alkene. Okay, then why? All right, so the cis alkene are less stable than trans because of a steric strain. Okay, do you guys still remember what is steric strain? Okay, so steric strain is as we learned, it's a repulsive interactions between non-bonded, that's important, non-bonded atoms in close proximity. And how many types of steric strain have we learned so far? So we have boat conformer, right? The boat conformer, do you still remember? Like the, yeah, I happen to have a model, see? So boat conformer, which has this white substituent and the red substituent close to each other. What is this called? Boat. It's a flagpole interaction, all right? And then also in the chair conformations, what other steric interaction have we learned? Like these three. What's these three interaction mean? 1, 2, 3. 1, 3 diaxial interaction, okay? These are basic steric strings we have learned, okay? So now we have a new one. We have a new one that exists in the cis alkene. So it's also a steric string. So for example, if you look at the this model, ball and stick model, so these two hydrogens, because of the cis relationship between two substituents, these two groups are really close to each other, thus have a steric string, okay? And pay attention, these two are not bonded, okay? They are non-bonded atoms that in close proximity. Non-bonded atom in close proximity. So that's steric strings, okay? Then, because the hydrogenation releases the strength of the alkenes, because it has a higher strength in cis alkenes, so it releases more heat during the reaction, all right? So I can show you this in 3D. So you can see because this cis, these two hydrogens are close to each other, and another one is we have this is a space filling. So this actually represents the actual size of the atoms. You can see, oh, they are clashing with each other. Okay, for this cis double bond, these two hydrogens is already close enough to clash with each other. All right, and for the trans alkenes, it doesn't have this problem, right? Because they are, for example, this group and this group are far away from each other, and this are also far away. And you can see this space filling is quite comfortable. Not two hydrogens, they are not touching each other. See, still some space here, not touching each other. Pretty comfortable. All right. So how about we extend the comparison of energies of all these types of olefins? For example, we have the acetylene. Okay, acetylene. So the heats is the released heat is 137 kilojoule per mole. Okay, that means it's most unstable. All right, and then the most stable one is the tetra-substituted olefins. Okay, tetra-substituted olefin is the most stable one, gives 111 kilojoule per mole. And you can see, you can summarize from this trend is that the tetra-substituted olefin is more stable than tri-substituted and more stable than di-substituted. And as we just learned just now, we learned that among di-substituted olefins, trans is more stable than cis because the cis has has the the steric string, right? And the least stable olefin is mono-substituted olefins. Okay, so you may wonder, okay, this has so crowded. This olefin is so crowded. Why is this more stable than this very least crowded one, right? So you can understand this comparison, but how do you explain the tetra-substituted one is actually more stable than the mono-substituted one? Okay. So let's recall briefly about what we learned, the molecular orbital description of the pi bond. Okay, so the bonding orbital is the same color, right? They are sharing electrons, and the anti-bonding orbital is the different colors, which are not bonding. Okay, and the reason why more substituted olefin are more stable than less substituted olefin is because a concept called hyperconjugation. Okay, the definition of hyperconjugation is the spreading of electrons from the filled CH orbital to the CC anti-bonding pi orbital. What does it mean? So if you have a simple ethylene, you have 4 CH bond, right? So the sigma bond is actually perpendicular to these anti-bonding pi orbital, which is different color. So you cannot align it, right? Because this bond is 90 degrees and this bond, there's not any overlapping, okay? But if you have a CH3 substituted at the olefin, okay? The CH3 now has 3 CH bond, okay? And this sigma bond can rotate. Okay, so once the sigma bond rotate to a degree that the CH bonding orbital is aligned with this pi anti-bonding orbital, and the color now matches. Okay, so the CH bond, it's a bonding orbital. It has electrons shared in this bond. Now it has an aligned empty orbital. Okay, so what does that mean? That means the electron has the tendency to go there. All right. Oh, the electron is telling each other, okay, we are so crowded here. So there is an empty like amusement park there. So let's all go there. So basically, the empty anti-bonding pi orbital has some interaction with the sigma bond here, and the electron spreading from the filled sigma bond to the anti-bonding pi orbital. All right. So pay attention that only those bonds that are aligned with the pi anti-bonding orbital have the same sign can share the electrons. Okay, then, so this is only one methyl situation, right? So the more substituents, the more stabilization by hyperconjugation. That means if you have a methyl here, methyl here, methyl here, then you can all share the field electron density to the pi anti-bonding orbital. And as we know that if you put the electrons on the pi anti-bonding orbital, it stabilizes it. Okay, it put the whole energy down. All right, and thus the tetra substituted is the most stable, while mono substituted is the least stable, and the ethylene is the least stable because it doesn't have any methyl or other substituent that has a filled CH bond or other bond that can share electron or spread electron to the anti-bonding pi orbital. Okay, so that keep in mind. All right, so reactions. We finally get to the part of we are going to teach you some new reactions about organic compound. Okay, so this chapter, we focus on the molecule, which is alkenes. We can see that alkenes can be transformed to different types of molecules. For example, it can become alcohol. It become, oh, what am I doing? Okay, it can become alkanes, like saturated, right? Alkane. It can become ether, become carbonyl compound, and haloether, alkyl halide, dihalide, halohydrate. Okay. We are going to cover all these transformations in this class. And when I was a graduate student, I heard somebody say that, quoted from Professor Barry Sharpless, that in organic synthesis, if you have alkenes, you have everything. Okay, so that there is specific reason that why Professor Sharpless says that. Okay, he is actually a Nobel Prize winner. Okay, and if you are interested, you can find out so what's his contribution to organic synthesis, and you will find out that Professor Barry Sharpless' work is highly related with alkenes, and so no wonder he says that if you have alkenes, you have everything, right? But it is true that alkenes is the foundation of many organic transformations. Okay, basically, because alkenes can be transformed to all the other groups, that if you have alkenes, you can build a lot of complex structures from alkenes. Okay, and if you see the syllabus of this course, you will find out that the alkene part is actually I think it is the biggest part of all the chapters, and because there are so many reactions we are going to cover, and also there is reason why this is so big is that before we introduce the reactions alkenes, we are going to give you a review about the reactions in general and thermodynamics and kinetics. Okay, so
first, we are going to review a little bit about types of organic reactions. So we can classify reactions by describing the overall change from starting material to product. Okay, so you probably already know this concept. We are just going through it very briefly. So addition reactions, you add two things up, right? So you two molecules at the beginning, at the end, only one molecule. You call it an addition reaction. Then the second one, elimination, then it's the opposite of addition, right? At the starting point, you have one molecule. At the end, you have two, okay? Then substitution parts from two molecule exchange. It's like for inorganic substitution reactions, you would say, for example, sodium hydroxide reacts with hydrochloric acid to form sodium chloride, salt, right? Parts exchanges. But in organic, we also have this concept. So, and there is also rearrangement reactions. So a molecule undergoes changes in the way its atoms are connected. So that means in rearrangement reaction, at the beginning, at the end, the component of the molecule doesn't change. Okay, but the position of each part of the molecule may change. Okay. And these are just the basic description of the chemical changes. And we have more specific terms that describe subcategories of each big categories. For example, for the addition reaction, we have conjugate addition, we have carbonyl addition, and the elimination, we have E1, E2, E1CB. As substitution, SN1, SN2, SNAR. Okay, a lot of to learn, especially, so you probably need to, for all the reactions I listed here, for you to fully understand every and single one of them, you probably need 2 or 3 years after you take the basic organic chemistry course and also these advanced courses like advanced organic synthesis, advanced organic chemistry and integrated organic synthesis. Okay. All right. So after we talked about this, we just do a small practice to warm up. Okay. So to determine the reaction type of these transformations. So the first one. So what do you think? So one molecule at the beginning, one molecule at the end. So the component of the molecule doesn't change. All these carbon. What changes is the position, right? So it's a rearrangement reaction. And the second one molecule at the beginning, two molecules at the end. 1 to 2, elimination, right? So so this what we call the acetal split into water and aldehyde, okay? And for the third one, two molecules become one molecule. 2 to 1, you add them up. Addition, right? Oh no, it's substitution. No, it's addition, yeah. And then we have the fourth molecule. You have sodium salt of this, and you have this molecule. Then you exchange this part, right? I think I mixed these two. Yes. So this one should be addition reaction. This one should be substitution reactions. Okay, that's right now. All right. So 2 become 1. You add them up. Addition. Okay. This exchange parts with each other, which is a substitution reaction. All right. So this is just a briefly review. Then after the reaction types, we have different reaction selectivities, right? And because in reality, real reactions do not convert reactants to one product in 100%. So if every reaction goes to 100%, researchers like us will be very, very happy. All right. So there are one situation is that there are products arising from another reactions. Okay, these are usually called a side product, or as other people may call it, byproduct. Okay, but even if one reaction occurs, there are a lot of possibilities, and that's why selectivity comes into play. Okay, we have regional selectivities. What does that mean? It means one reaction generates two products, and the two products, if they are constitutional isomers, and we can call them regional isomers. And if more B is formed than C, we can say it's a regional selective reaction because we generate, even if it's a little bit more B than C, we call it a regional selective reactions. Okay? And the definition is based on that B and C are constitutional isomers. Okay. Then we have another one called a stereoselective reaction. Okay, what does that mean? That means A generates B and C. but B and C are not constitutional isomer. They are now stereoisomers. Okay, they can be enantiomers or they can be diastereomers. So if a little bit more B is formed than C, we can say this reaction is a stereoselective reaction. Okay, so the difference between regioselective and stereoselective is the relationship between B and C. One, in the regioselective case, is constitutional isomer. The other is stereoisomers. All right. So what do we want to know about the chemical reactions? Okay, we want to understand the chemical reactions on a molecular level. So that is different from, I would say, biological science or real life. Okay, so we want to learn the changes in the molecular structure, bonding and the bonding changes. So we have a starting material, we have the product. So we want to say, okay, how these atoms are connected, do they change? And what's the change? How does it happen? Okay, so in real life, we have reactions, right? So for example, this adorable but like a picture shows that reactions in real life, reactions in life, okay? A cat bites a dog, the dog is scared, okay, we describe it, it's a reaction, okay, the dog reacts, okay? And we have reactions described in biology, so which I'm not quite good at, okay, good at it. So we have different proteins, maybe, I don't know, this is membrane, whatever. So, but what we want to know is reactions molecular level, all right? So this part is what we are going to focus here. So we can say this is starting material, okay? Okay, this attack here, okay, bonding of the molecule changes, right? And this is the product. You can see, oh, this bond seems new, right? So we wanted the molecular structure shown. We wanted the bonding shown. We want the change in structure and bonding shown. Okay, we want to see the starting material, its structure and bonding. We want to see the product, its structure and bonding. We want to see how the starting material become the product and how the bonding change gradually. All right, so so we want to know, see, just as I said, we want to know why and how it happened, right? And particularly important concept here are thermodynamics and kinetics. So for example, from Y to Z, the thermodynamics consider like how much Z is formed, all right? What's the equilibrium and what's the equilibrium constant? What's the ratio of Z divided by Y, right? And for the kinetics, we focus on different aspects of the reaction. We want to see also, okay, we know Z is formed in how much amount, but is Z formed in this kind of amount, like, does it need 100 years or does it like 5 seconds, right? So that's the kinetics, how fast is the reaction, okay? And we want to learn what's the mechanism behind the Y to Z transformations, okay? So for example, we know that the mechanism describes the changes in bonding, right? But how many bonding are changed? In what order? How fast is each bonding changes? And what's the stereochemistry of each bonding changes during the process of the reaction? Okay, so again, we are not actually moving into teaching you new reactions right now, okay? But we are going to build a foundation, which is telling you how to describe and draw reactions first, okay? Because we know a mechanism can be one step or sequence of steps, okay? Then we define that one bond forming or breaking event is one step, all right? In one step, a bond forms or breaks, okay? And so two concepts is this bond making and breaking occur sequentially, the reaction is said to be stepwise. But if it occurred at the same time, it's concerted. All right, so let's see example. So one bond breaking event. This is you should know this reaction, right? Hydrochloric acid dissociation, right? Which bond break? This hydrogen Cl bond breaks, right? Becomes proton and chloride anion. All right, this is one bond breaking event. So how about bond making? The same, simple reactions. If a proton reacts with a hydroxide anion, it becomes water, right? So a bond forms between the proton and the hydroxide anion here. So that's one bond making event. All right, so how do we draw this? So we know the net result is the bond breaks, but how does that happen? So So because bond making and breaking events, involves relocating electrons, so the complete mechanism we draw to describe the reaction must show electron movement. Otherwise, we don't know otherwise people won't understand how did that happen. So for example, you have a neutral hydrochloric acid. The electron within this bond apparently moves somewhere else because the bond breaks, right? So we know that the electron goes to chloride because now the chloride becomes an anion. The hydrogen loses its electron to becomes proton, right? And now here, the hydrogen does not have any electrons, but in the end, it shares an electron with oxygen. So where does the electron come from? It comes from the hydroxide anion, right? So this pair of unbounded electrons just goes to the proton. Okay, very, very simple examples. So the curved arrows we draw here indicate electron flow, okay? Arrowheads with a complete head indicate electron pair. So if you have a complete head like this, it means moves two electrons, okay? Not a single electron, but a pair of electrons. And the arrow shows the direction of electron pair flow. So that means this pair of electrons moves to the proton, not the opposite way, okay? Because the opposite way cannot happen because the hydrogen does not have any electron to give to hydroxide. So in the hydroxide has the electron, it gives to the proton to form a bond. All right, so almost all these organic reaction happens because there is different density of electrons. And the different density of electrons originally comes from the electron negativity. Okay, because there is a difference in electron negativity. For example, the fluoride electron negativity is so high, if it forms a bond with other, it draws electron from others, right? And so for example, if the lithium the electron negativity is so low, so when it forms bonds with other element, it gives out electrons. Because the other elements is drawing electrons. So the unsymmetric local electron distribution of molecule gives what we call dipole, right? This is what we learn because some part of the molecule draws electrons, some part of the molecule gives out electrons, so there is dipole. And within different molecules, like if they have dipole, they have a dipole-dipole interaction. So that's what we learned in the last chapter. But here we are going to learn that because these uneven or unsymmetric local electron distribution, we can have now reactions. Okay, not only we have some small interactions, because these electron density are different, we can now have reactions that involves bond breaking and making. All right. So we have again some example about polar bonds and the regions. All right. So electron activity difference, as we said, leads to a partial negative charge and partial positive charge. For example, chloride. What's the electron negativity of chloride? It's 3.0. How about carbon? Carbon is 2.5. So the chloride has a higher electron negativity than carbon, right? So that means the electron moves towards chloride. Okay, you can see this electron density map. Again, the red one means the electron density is higher. Okay, so the chloride draws electron here. That means it's a partial negative charge. All right, then goes to this example. We just said lithium tends to give out electrons, right? So the lithium carbon bond, actually the electrons goes to carbon instead of goes to other way. So this carbon gives out, this carbon accepts electron. So in this molecule, it is polar, but the partial negative charge is on the carbon. Okay, so that's so you can see the chloromethane and the methyl lithium looks like similar, but the internal distribution of electrons are totally different. All right. So polar bonds can also further increase in polarity by interacting with solvents. Okay, for example, what's this molecule? Methyl or methanol, right? And methanol can actually react with an acid. So it happens this way. So the oxygen of the methanol has a long pair, right? It has electron, it's one, and it can react with an acid to accept a proton. So it gives out electron, accept a proton to become this protonated methanol. So now the protonated methanol has a positive charge now. And the positive charge it wants electron, right? Because it's positive. If you are negative, you don't want electrons. But if you are positive, you want electron to come to your way because it attracts electrons. Okay, so it become from weakly electron. It become weakly electron poor carbon to a strongly electron poor carbon because of the protonation event. Right, then we can say that methanol is activated by an acid. So here are two new concepts. Is that if a nucleophile, if a species is rich in electron, okay, we call it a nucleophile. It's an electron-rich species, and because it has electron pairs to donate, from the concept of acid and base, we call it Lewis base, right? Because Lewis base donates electrons, and the nucleophile is electron-rich. It's ready to donate electrons. Okay. For example, all these nucleophiles I have listed here. So, sorry about all these typos. All right. So you can see all these listed nucleophiles have a pair of electrons to share. For example, the chloride, anion, right? You have 4 pairs, right? The hydroxide, water has 2 long pairs on the oxygen, and ammonia has a very strong long pair that can donate it, all right? And opposite is electrophile. So electrophile is an electron deficient species. It's ready to accept electrons. So electrophiles are Lewis acids. They usually, if they have they usually have positive charge, like this hydronium, right? It's a proton, and it's positive. It's ready to accept the electrons. Or they have a partial positive charge. For example, we just learned that because there's a halogen is more electron negative than carbon. It draws electron to the bromide, and this has a partial positive charge, which is ready to accept electrons from other species. Then this is an electrophile. And this carbonyl, which is C double bond O, because the O is electron withdrawing, so the carbonyl carbon has a partial positive charge, can accept electrons. Another scenario is that if a molecule has incomplete octet, for example, like trichloroaluminum, so which is it can accept the electron because it has an incomplete octet. Okay, it's a very strong Lewis acid. And I remember I showed you this example when we reviewed the concept of Lewis acid and base, that the trichloroaluminum can react easily with diazo ether. Okay. The same with the borane. So they are both very strong Lewis acid, incomplete octet. That's a very good electrophile. So just like acid and base, it is also possible for a compound to act both as a nucleophile and as an electrophile. And whether it is nucleophile or electrophile really depends on the reaction conditions and the reaction partners. Okay, for example, water. So we just say water has a long pairs, right? There's long pairs. It can react with it can act as a nucleophile and react with an electrophile. Okay, on the left, but water also has a H, right? This H can act as proton, all right? So this can also act as an electrophile and then react with a nucleophile to give the, for example, this methyl anion. It can attack this proton, give back the electron to oxygen to form methane. So basically, for 2 different regions you can see the water, the same molecule can act as a nucleophile or as an electrophile. Okay, then how to draw? So we have a nucleophile that has rich electrons, right? Rich in electrons. Then we have electrophiles that is deficient in electrons. So those would react with each other as we show. Okay, then how do we describe this kind of electron flowing? Okay, then so this is how we learn that arrow pushing. Okay, so the arrow goes from the nucleophile, which is rich in electron, to show the donation of electron pair to the electrophile sink, electrophilic sink, which is E, usually simplified as E. The nucleophile usually simplify as Nu with a pair of electrons, because you want to always show that the nucleophile has an electron to donate to E. E, you don't have any electrons shown here when you put it simple. Okay, so oxygen lone pair nucleophile, right? Donate an electron, a pair of electron, which is arrow, full arrow, a pair of electrons to electrophile. Nitrogen, right? Carbon anion, okay, to electrophile. Okay, and then if you have a nucleophile and an electrophile, for example, this carbocation. So the nucleophile has a lone pair. It can, using the arrow to go to the carbon. Nucleophile can go to the partial positive charge carbon, and this bond breaks to give electrons to this partial negative carbon, the X. The nucleophile can also extract a proton, and the electron of this OH bond goes back to the O. And the nucleophile can also attack carbonyl compound, which gives a one bond into the oxygen. The electron goes to the partially negative charge of the oxygen. So one thing to keep in mind that the arrows show electron pair movement, not atom movement. So arrow must originate from lone pair negative charge or bond. Only three. Okay, you cannot make the arrow start from oxygen. Okay, so I will show you several examples to describe these arrow pushing. So you cannot draw a arrow from the oxygen to E. You have to draw it from the lone pair of the oxygen to E. Okay. Then you also need to keep in mind to keep track of valencies and the charges in order to make a correct arrow pushing for the reaction. Okay, so for example, you have a negative charge here, right? You react, so the methoxyanion react with hydroboric acid, and so it starts from a lone pair, all negative charge, to the proton here, and this bond breaks. Okay, you have to draw the breaking of this bond. Why? Because this hydrogen already has 2 electrons here. When another electron pair moves to the hydrogen here, the electron pair of the H bond must leave to keep the hydrogen, because the hydrogen can only have 2 electrons, right? Right? Because if you form a bond from the O and the H and still keep this bond, the hydrogen is linked to 2 substituents. That's totally wrong. Okay. And another thing is that keep track of the changes in charge. Okay. So in the beginning, you have a negative charge. In the end, you should have a negative charge. So if you draw a reaction arrow pushing, you found out in the beginning you have a negative charge, but in the end, you add all these charges together, found out it's positive or it's neutral. Something is wrong. Okay. Okay, let me show you several examples about arrow pushing. Okay, so what we have as the first example is this reaction. So we have a carbon bonded to methyl and 1 oxygen anion and bromide. It becomes a ketone and bromide anion. All right. So the incorrect way to draw this arrow pushing is you break this bond and form this bond. Okay. Why is this wrong? All right. First, the oxygen is electron rich, right? It has negative charge. So the arrow usually starts from something electron rich to something electron poor. Okay. So it should be the oxygen that starts the arrow, not accept the arrow, okay? And the second one, why is wrong, is that if you draw this way, the ketone actually becomes 2 minus. Okay, it becomes 2 minus because it accepts another pair of electrons, right? So this is totally wrong because this is a neutral molecule. It shouldn't be 2 minus, okay? And for the bromide this bond to break and the bromide to give out an electron is also not reasonable, because bromide plus is not reasonable in this case, right? So first wrong is that the arrow goes from the nucleophile to the electrophile sink. So that means the arrow should start from here. So the correct way to draw this is that starts from the minus or start from lone pair to go back to this bond, okay? So you form a double bond here. But once the double bond is here, something concerted must happen. The bromide must leave, because if you have a double bond here, the bond is still here, you have 5 bonds. That's bad for the carbon. It's wrong for the carbon. So once the electron goes to this bond breaks, and this arrow originates from a bond. It's okay due to an atom, which gives a bromide anion. All right. Second example is the deprotonation of the positive charge here. So you have protonated methanol, you want it to become methanol. Okay, positive become positive. The wrong way to draw this is what? Is that this bond break but give electron to the hydrogen. Why is wrong? Because the arrow must go from the nucleophile to the electrophile. So the oxygen is already positive charge, it's an electrophile, okay? It doesn't want to give away electrons anymore, it's deficient in electron, it wants to accept electrons, all right? So what do we do? So we put this bonding electrons to the oxygen, okay? Then oxygen is very happy because it was electron deficient, now it has a pair of electrons. So it becomes a neutral molecule, and the hydrogen loses its electrons, become a proton. Okay. Okay, third examples. Another protonated species, but now it is ketone. So if the ketone is protonated, positive charge to positive. The wrong way to draw that is that, okay, the net result, the hydrogen leaves, right? So we just, the hydrogen just go away. So why is this wrong? This wrong is that the arrows must show electron pair flow, okay, not atom movement. You cannot ask this hydrogen to leave, okay? You need to start the arrow from a bond or a long pair or a negative charge, okay? So the correct way is that you start from this bonding. And another wrong with this drawing is that you have an electrophile here, right? The oxygen, again, like the proton in the methanol, it wants electrons. So you start from a bond, then you goes to the electron deficient species of the molecule, which is the oxygen plus, okay? Once the oxygen accepts a pair of electrons, it becomes neutral, and the hydrogen leaves, become hydrogen, because it loses this bonding electrons. Okay, final one. So we have an olefin. So we have hydroboric acid. Okay, it seems like the proton here goes to the olefin and the bromide is left. Okay, so what we know? We know that the olefin is electron rich because it has a pi bond, right? It has a pi bond that's a weaker bond than the sigma bond. So if all the bonds in this molecule is considered, the pi bond is easiest to break because it has the lowest bonding energy. All right, something breaks here. So the wrong way to draw this. So don't do that. Okay, so you see that the hydrogen goes to the carbon, so that means the carbon has the hydrogen. So you draw an arrow from the carbon to hydrogen. That is wrong because the arrow must originate from only these three things: lone pair, negative charge, or bond. So just as I said, because the pi bond is easy to break, the electron can go to the proton, right? So the pi bond electron starts here, goes to the proton, and remember this is an electrophile, right? Because the bromide is high in electron negativity, so it has a partial negative charge. So if this electron goes to the proton, this bond must break. Proton cannot have two bonds. So this bond break gives bromide anion. The bromide leaves with the electron. The proton goes to here. The olefin or the pi bond has the proton. Then you have a positive, you have a negative. So this type of mechanism, which an alkene is protonated by an external acid, is a very important step in a lot of the reactions we are going to learn at the later part of this chapter. All right, so the only way to be good at this arrow pushing is practice. Okay, so on the page 261, there is an essential skill tutorial, all right, about drawing curved arrows, and it has listed several problems that ask you to draw the electrons. For example, ask you to draw the electron pushing or arrow pushing electron flow of these reactions. Okay, so you know that the bromide is high in electron negativity, so this has partial negative charge, so this bond must break, so you draw here, right? Okay, so if it's highly recommended that you practice, on this, okay? And you can go to your book and practice on all these problems, okay? That will make you a master of drawing arrow pushing, and really essential for the later learning of all these reactions and all these reactions of alkenes and the other compounds. Okay, so after we learn how to draw the reactions, we also need to briefly review the thermodynamics and the kinetics, and we are going to teach you something new about these two concepts in the context of organic transformations of carbon-based compounds. So we will review and apply the following concepts. You should have already learned all these concepts. So for example, Gibbs free energy, enthalpy, entropy, rate law, first order, second order, rate order, right? And then rate determining steps, usually we call it RDS abbreviation. And activation energy transition state is more related to organic compounds we are going to show you here, okay? So will a reaction occur, and what's the indicator? So this is Gibbs free energy equation. It is very important in general chemistry, and it determines whether a reaction can go or not. So this one is the Gibbs free energy change, okay? So it's defined as the energy difference between reactant and the products. So when delta G is negative, it's called exogonic. It's favorable equilibrium constant, the reaction occurs spontaneously. So on the other way, so if delta G is positive, it means that it's unfavorable, all right? It cannot occur spontaneously. So it's a comprehensive effect from the delta H and the delta S. Okay, so but this is the golden indicator for whether a reaction will occur or not. So we also have the heat of the reaction, which is the enthalpy change. Okay, so this only determines whether a reaction is release heat or absorbs heat. Okay, when it's negative, it releases heat. Okay, and when it's positive, it absorbs heat. And the entropy is the change in randomness. Okay, so it's like the real life. If your room is messy, we say, oh, the entropy of your room is really high. Okay, very nerdy way to say this. And so when the delta S is negative, that means the randomness of the reaction decreases. When it's positive, the randomness increases. Okay, so a delta S in combined with the temperature of the reactions and contribute to the free energy change. Okay. So another thing is the reaction coordinate diagrams. We are going to see this a lot in the following classes. So at the left, you have the starting material, and this level is the free energy level of the reactant. And on the right, you have the product. Now A is not connected, B is connected to C, okay? This is the free energy of the products, okay? So the x-axis is the reaction coordinates, showing the progress of the reaction, and the y is the Gibbs free energy. It's not enthalpy or entropy, it's the delta G, okay? The Gibbs free energy. And in organic reaction, we will see that there is a moment when the bonds between A and B are partially broken, and the B and the C bond are partially formed. So what we call it is a transition state. We are going to learn it later. So, okay, besides the Gibbs free energy, we are going to put it more complicated. We now have the Gibbs energy difference between starting material and the transition state. So the transition state is the highest point on the reaction pathway that is bonds partially broken, okay? So in this diagram, so delta G is what? So delta G is the energy difference between here and here, okay? But the delta G, the free energy of activation, it means the energy difference between here, starting material, and the transition state. Okay, so the delta G0 here means that whether the reaction will occur and is it favorable or not. But the free energy of activation indicates how fast the reaction proceeds. That means kinetics. Okay, so we can learn kinetics from this indicator instead of the Gibbs free energy. So just as I write here, so knowing the value of delta G only tells us whether equilibrium favors product formation. Theoretically, it does not tell us how fast. So if a reaction, you say from thermodynamic, okay, if A plus BC is much lower than A B plus C. Okay, you say, oh, the reaction will occur, but how long? We can't wait 100 years for a reaction to complete, right? Okay, so there are several situations. So for the exergonic reactions where the Gibbs free energy is negative, so the product is more stable than the starting material, yeah, right? But even if it has the same Gibbs free energy change, it can have a different transition state energy, the free energy of activation, okay? And for endergonic reactions, when delta G is positive, delta G zero, I will just call it delta G zero, is higher, is positive, but it can still have a much higher free energy of activation and a lower free energy of activation. Okay, so in these two, the overall reaction is favored, but this reaction must be much slower than this one. Okay, in this reaction, these two reactions, the overall reaction is not favored because the Gibbs free energy change is positive, but this reaction is still much slower than this one because the free energy of activation is higher than this one. Okay, so for the transition state I just introduced to you, I'm going to reinforce the concept here. So it's the structure of at the point of maximum energy, which is listed here. Okay, it has partial bond formation and cleavage, and unstable, cannot be isolated or observed. So as an educated undergraduate in organic chemistry, okay, so there's one thing I'm particularly interested about is that when some people tell me that, oh, we can isolate the intermediate and we can isolate the transition state. So this really pissed a lot of people off because a transition state in definition cannot be isolated. Okay, it's like a very transient intermediate. It's not intermediate. Very transient state of a molecule. Okay, so it's basically cannot be seen or cannot be isolated. Only you can say I can isolate the intermediate. You cannot say I can isolate the transition state because by definition it cannot be isolated. Okay, then the free energy of activation delta G design is the energy difference between the starting material and the transition state. Okay, and it's different from the energy difference between the starting material and the product, which is the free energy change. It gives free energy change. Okay, it's not the free energy of activation change. Okay, so it's the energy difference between reactant and transition state. Keep that in mind. And if this can be surmounted by the reactants, then the reaction can proceed. Okay, so that means if your molecule has enough energy to climb to the transition state here, okay, it can easily fall down to here because it already overcome the greatest barrier of the reaction. Okay, sometimes in most cases you need to heat the reaction to surmount the energy barrier here because at room temperature your molecule just stayed here. If you heat it, energy, then come here, it can go forward. All right, so I think the time is up. And in the next class, we will keep learning the reaction coordinate diagram in a more complex system. And also we will start to talk about individual reactions of the alkenes, which gets much more interesting, right? And I hope you are still with me so far. And also, before we finish here,